Hi, everybody. This time we're going to talk about activation energy in chemical reactions. Now, some chemical reactions just spontaneously occur. You mix vinegar and baking soda together, and it is just going to foam all over the place and produce a lot of wonderful carbon dioxide gas. But some chemical reactions don't. You have to give them a little bit of kick. You've got to give them a little bit of energy before they begin. Let's talk about matches. If you have a typical match, there are two chemicals. There is a chemical on the tip of the match. There is usually a chemical on the side of the box of matches, and you need oxygen in the air. So right here, we have all of the chemicals necessary, and you can actually have them touching each other, but they don't spontaneously react. You have got to add that little bit of spark. You have got to add that bit of friction in order to make that chemical reaction begin. Now, that energy you have to put in to kick that reaction into going, that's called the activation energy. The official definition is energy needed to begin a chemical reaction. And when we were learning how to write chemical reactions, we very often included that information above that yield sign. If we put a little triangle there, that meant heat. But sometimes activation energy can be light. Sometimes it needs to be electricity. But some reactions, you just got to give them a little oomph in order to get them going. Now, why is activation energy necessary? Well, keep in mind, in order for atoms to bond, they have to actually hit each other. There has got to be a collision between those atoms in order for those atoms to have a chemical reaction. And the hard outside candy coating, it's not hard, but the outside candy coating on atoms is the outer electron shell. And if you've got atoms and molecules that are bumping into each other, they have these outside electron shells, and it's sort of like bumper cars. These electron shells are going to bounce off of each other if they don't hit with enough speed. They hit with too little speed and boop, they're just going to bounce one off of another. The reactants are moving too slowly. Well, slow in chemistry means cold. And you have to add some more heat. You've got to give them some more kinetic energy and some more speed. If the reactants are going fast enough or hot enough or have a high enough kinetic energy, when they collide, there is enough energy to break into those electron energy level shells, and the electrons can interact and bonding can occur. It's sort of like you've got to hit these cars with enough oomph in order to get their bumpers to lock. Same thing with a chemical reaction. You've got to hit them hard enough to make things begin. Now, for a lot of chemical reactions, room temperature is going to be hot enough for there to be enough chemical energy in order for the reaction to appear spontaneous. You pour things together and whoop, off she goes. But sometimes it's not. You have to add some sort of additional energy to make it go. Now, we picture this whole situation using what are called potential energy diagrams. Sometimes they are called reaction progress curves, and I've heard some people call them activation energy diagrams. So it depends. You will hear all three terms used, but we use them to visualize the energy changes in the reactants and the products in a chemical reaction. Here's how they look. If we take the energy of the reactants in a chemical reaction, where do we calculate? How do we figure out those energies? Remember when we looked at these charts of kilojoules per moles of the chemicals involved in a reaction? So we look at the energies of the reactants in a chemical reaction, and then we look at the products in a chemical reaction. And again, we calculate that energy per mole of the reactants. We can look at the difference in energy between the reactants and the products, and that difference there is the amount of energy that is going to be released by that reaction. But there's a wacky step in between. And the wacky step in between is this bit right there. This bit right there is a mathematically measurable amount, and this is the activation energy. This is how much extra energy you have to put in order to make the reaction occur. This is a great illustration. This person is trying to get this rock to the bottom of the hill. Unfortunately, there's a little hump in the way. So they have to add extra energy to push it to the top of the hill. And once they get it there, gravity takes over and the boulder is going to roll all by itself. That's this concept of activation energy. You have to add a little bit of extra energy to get it up to the point that it will occur spontaneously on its own. Now, the larger the activation energy hill, the higher the amount of activation energy present. And on this week's study guide, you're going to look at a couple of these different activation energy diagrams. And for example, if we take a look at this one labeled A, the difference between the reactants and the products, there is a small hill, meaning that the activation energy that has to be added is relatively low. Doesn't take a big input of energy to get the reaction started. For reaction B, the difference between the reactants and the products is a very large hill, and so this has a high activation energy. That means you have to really kick those reactants with an awful lot of kinetic energy, typically an awful lot of heat, in order to make this reaction occur. But the other piece of information that's buried in here is how much energy the reaction is going to output. So let's take a look at the amount of energy each reaction is going to output. Reaction A has a really big energy output. It's the difference between the reactants and the products. So this has a large energy that it is going to produce. The energy output between the reactants and the products here is very, very small. Not a big energy output, and it's hard to get going. So some reactions are going to be better in some applications than others. Now, exothermic chemical reactions are reactions that give off energy. These are reactants that feel warm to the touch or feel hot to the touch. These are combustion reactions. In an energy diagram, one of these potential energy diagrams, when we look at the energy of the reactants and the energy of the products, you'll notice in an exothermic reaction that the reactants have more energy and the products have less. So if we calculate the energy of the reactants, the energy of the products, there is always energy that is released. And this energy that is released, this comes out in the form of heat that is given off. The larger that change in heat, the more heat and the more energy is given off. This has a smaller change in energy, and this is going to be a lower or a less amount of heat that is given off by reaction B in this illustration. There are also endothermic reactions. Endothermic sounds to me a lot like into, and thermic meaning heat. So these are chemical reactions that absorb heat from the surroundings. And the chemical reaction that is common, that you've probably had some experience with, is instant ice packs. These are the things that you buy at the pharmacy, or you might have in a sports bag if you've played some sort of sport. There are two bladders, one inside of another, and when you break the inner bladder, the two chemicals mix. There's a chemical reaction that occurs, and because of that chemical reaction, it absorbs heat from the environment as these two chemicals mix. And it feels cold to the touch, and it's a wonderful instant cold pack when you're on a sports field and you can't have a bucket of ice right there for an injury. In one of these endothermic chemical reactions, the products are going to actually have more energy than the reactants. So the diagram is going to look like this. Here's my reactant, here's my product, and heat is actually taken in. So you're going to have heat that is actually absorbed from the environment and that is going to be an endothermic reaction. Here's another picture of an endothermic reaction. Here's my reactants, here are my products, and here is a quantity of energy that is absorbed because of this chemical reaction. So you have both exothermic and endothermic. We talked quite a bit this week about petroleum and fuels. And remember, we talked about small hydrocarbon chains like methane, ethane, propane, butane. And as you get longer chains, octane, kerosene, diesel, you end up with longer chains that have more energy that is released the longer those chains get. But here's another real interesting part about this. The longer the hydrocarbon chain also means that they are harder to ignite. They have larger activation energies. So let's talk through this. If you have a little molecule like methane, and forgive my drawings, they're me attempting to draw on a computer. So if you have methane here, small activation energy hill, very small change in energy that is produced. How do you ignite a gas stove? Well, a match. You can just do this with a simple little flame. It's pretty easy to ignite methane. But you also get a small amount of energy released. If you use propane, you're going to get a bigger change in energy. It is going to be a bigger molecule. You've got 3 carbons in that chain. It's going to give you more energy, but it also has a bigger activation energy hill. It's a little bit harder to ignite. By the time you get to octane, 8 carbons long, 1, 2, 3, 4, 5, 6, 7, 8, much bigger molecule in an octane blend gasoline, much bigger quantity of energy that is released when you burn that in your car. But you also have to put those molecules under compression inside of pistons in order to make that combustion happen. Bigger activation energy hill. Kerosene, jet fuel, Jet A. Those jet fuels, you have a much bigger change in energy. If you're going to power something as big as a jet, you want a good, powerful molecule. You use a longer hydrocarbon, but it's harder to ignite. So you have to kick it a little harder, add more activation energy. And then diesel, long hydrocarbon chains, big amounts of energy, huge amounts of energy that are used. And that's why we use it for 18-wheelers and diesel trains. But it has a huge activation energy. How do you know this? Well, have you ever heard of glow plugs? When truckers in the wintertime go into diners, they do not turn their trucks off. Why? Because these molecules are so long that they are going to gel up and they are going to get goopy. And you cannot put goop through a diesel engine. They have such a huge activation energy hill that they have to keep this fuel warm and viscous so it will flow, and they have to hit it really hard. And that's one of the reasons why diesel engines are very expensive. The compression, everything inside of those engines has to be larger and more beefy in order to make those big activation energies. One last idea before we leave, and that is, why is old gas hard to start? I don't know about you, but the beginning of every summer, trying to start weed whips, trying to start gasoline motors, it's always tricky to start those. Why? Well, when you buy gasoline to put in these things, they are a blend, and they're a blend of a whole bunch of different hydrocarbons. Some are low and some are high. Well, if you have old gas, what happens is those low volatility hydrocarbons, the C5s, the C4s, the C6s, these are going to evaporate sooner. When you have fresh gas is a mixture of all of these, and the fresh gas is going to be easy to ignite because those carbons that are small chains are going to have low activation energy hills, and they are going to ignite easily, and once they're ignited, they're going to take everything else with them. But old gas, these small ones are going to have evaporated, and all you're going to have left are those big hydrocarbons like C10s and C12s. And honey, you can pull the chain all day long and you are not going to ignite that. All right, see you next time and have a good one. Bye-bye.